Hello students, today I am going to discuss another problems on fluid mechanics based on the Archimedes principle or force of buoyancy. The question is a uniform cylinder of length L and mass capital M having cross-sectional area A is suspended with its length vertical from a fixed point by a massless spring such that it is half submerged in a liquid of density sigma at equilibrium position. The extension x naught of the spring when it is in equilibrium is, these are your options. So question to কোৱা হৈছে যে we have a uniform cylinder. আমাৰ হাতত এটা uniform cylinder আছে. That cylinder is dipped in a liquid of density sigma. A liquid of density sigma. This is our cylinder, suppose. This is our cylinder, and this is dipped in a liquid of density sigma. And how it is dipped? Half submerged. Half submerged means the cylinder is submerged by half of its length. Cylinder to adha yat submerged hoye ase. ঠিক আছে, cylinder adha submerged hoye ase. Etia aru uporo pora cylinder to it is connected to a spring. Vertically enake throa ase. It is connected to a spring and it is then dipped in a liquid of density sigma. So in question it is given the cylinder is in its equilibrium position. So what are the force acting on this cylinder? The forces are, we need to draw the free body diagram of this cylinder while dipped in the liquid solution of density sigma. So first one is your spring force. As spring is extended, the spring force, let the spring force be kx naught, assuming that x naught is the extension in the spring in its equilibrium position, extension in the spring in its equilibrium position. Since it is extended, so force will be in the upward direction, and because of the liquid of density sigma, since it is submerged in the liquid, so it will have a buoyancy force upward. Eta force lagibo, buoyancy force eta upward lagibo because of the Archimedes principle, as we all know that. So that is equal to, what is the buoyancy force? I think it is denoted by T. So buoyancy force buoyancy, as you know, it is mass of the liquid displaced into g. Okay, it also acts upward, and in the downward direction there is the weight of the body or weight of the cylinder, that is mass into acceleration due to gravity. Now this buoyancy is equal to ml into g. Mass of the liquid displaced is your density of the liquid displaced, and volume of the displaced liquid into G. Now, density of the liquid, now volume of the liquid displaced is equal to volume of the body submerged, or you can say submerged volume of the body, volume of submerged portion of the body into G. So you can write it as rho L, density of the liquid. Here it is given as, this density of the liquid is given as sigma. Volume of the submerged portion will be equal to area of cross section of the body, and its length is given as capital L, so it is L by 2 because it is half submerged into G. So this is your volume, A into L by 2. This is the volume of the submerged portion of the body, sigma A L by G. This force also acts upward. Now at equilibrium, the upward force will be equal to downward force. So now at equilibrium, net force is 0, that is upward force is equal to downward force, means we can say net force is 0, or we can write it as F net equal to 0 on the cylinder, because cylinder is in equilibrium. So if we put this, we have kx naught plus buoyancy force is equal to mg. This implies kx naught plus sigma al by 2 into g is equal to mg. From this, if we calculate, let us calculate this, kx naught is equal to mg minus sigma a L by 2 into g. So x naught is equal to mg by k minus sigma a L by 2 into g. Okay, now if we take mg by k common, we will get 1 minus sigma a L by 2m. So the extension in the spring at its equilibrium position is given by x naught equal to mg by k 1 minus a sigma L by 2m. So if we go to the options, then option 2 is the correct option. So this is your correct options. Thank you.